Hello. Today we're going to take what we've learned with one-dimensional physics and one-dimensional kinematics, and we're going to apply that to more than one dimension. The real world contains 3 dimensions, although lately it's been quite popular for physicists using string theory to talk about and describe the world using upwards to 13 or 14 different dimensions, I think. But the 3 that we deal with most in high school physics is simple up and down motion, forward and back motion, and side to side motion. And in fact, in our class, we're only going to ever deal with problems in 2 dimensions, although 3-dimensional things is really no different. You can apply the same techniques we use for 2 dimensions into 3 with no difficulty. The good news, there's no bad news really. The good news is that there are no new formulas necessary. The formulas we've learned so far will also help us in multiple dimensions. It's just that we're going to have to use them more than one time. So the main idea is that dimensions are independent of each other. That is, the motion in one dimension does not really affect the motion in a different dimension. How can we use this practically? We use this by treating each dimension separately. And in fact, the only thing that the dimensions have in common is time. So you've seen how we've used a list of different types of kinematics quantities before. We'll do the same thing now, except we'll have 2 sets of quantities. Usually we have a horizontal and a vertical dimension that we're talking about. So we'll have a list of quantities for the horizontal dimension. Then we'll have a list of quantities for the vertical dimension. And if you notice, I put time in the middle because it is independent of dimensions. It's not a horizontal dimension, nor is it a vertical dimension. In fact, it's the common link. So here's an example. We're going to roll a ball off of a shelf or a desk and see that it lands a certain distance away. And what I'd like to do is to go backwards and figure out how fast was the ball rolling as it rolled off the shelf. So there's a picture. Got a ball on the shelf. It has some sort of a velocity, and as soon as it leaves the shelf, then it starts to fall, and it hits the ground. We know the height and the distance that the ball traveled. The height was 87 centimeters, and the distance away from the shelf was 27 centimeters. So here's a picture of what's going on. Now let's come up with the list of different quantities for this particular problem, and then start to use some of the formulas to solve for what we're missing. Horizontally, we know the final position. The final position horizontally was 27 centimeters, or 0.27 meters, about a foot. We don't know the initial velocity. That's what we're looking for. And I don't see any other things here that they've told us about either. Let's look at vertical. Vertically, we know its initial height, or its initial position, was 87 centimeters, or 0.87 meters. We know the final position was 0 because it hit the ground. We'll call the bottom here 0. We don't know anything about its velocities. It doesn't say anything about its acceleration either. Now, a lot of times in physics, we're going to need to make some assumptions that are not specifically mentioned in the problem. For instance, we've done this many times before. We've called an initial position 0. In this particular case, they didn't say anything about horizontal initial position, so we can assume that that's 0. It also didn't say anything about an acceleration horizontally. Typically, there isn't horizontal accelerations unless you have to consider air friction slowing it down, or if there's some sort of a rocket involved that's pushing it along, or some other outside force. Since it didn't mention anything about an outside force, we're going to assume that there isn't one, and that the acceleration horizontally is 0. It's a very common assumption to do. Vertically, there are some assumptions that we need to make as well. Most importantly, we don't know exactly where this occurs, but we can assume that it occurs on Earth and therefore it accelerates at the rate that all things on Earth accelerate at, and that's 9.8 meters per second squared. That's a downward acceleration, so we need to use negative 9.8. Another assumption that we need to make is that vertically this object had no speed initially, that it was rolling completely flat. It didn't say anything about a vertical velocity or that it was rolled at an angle or anything like that, so that's a safe assumption to make as well. The final velocity is not going to be zero. It certainly hit the ground going downward, but we don't know what that speed is, and honestly we don't need to know what that speed is. It's not necessary to know how fast it is going when it hits the ground in order to calculate how fast it was going when it left the shell. In most problems like this, our first goal is to figure out time. Time is what links the vertical and horizontal dimensions together. Most of the time in a problem like this, you know enough information vertically to calculate for time, and then we can use that to calculate things horizontally. Vertically, it looks like we know everything in the so vote for AT&T formula except for T. And so that would be a suggested place to start. Typically, when I'm working with multiple dimensions, I like to write which dimension I'm working with and then the formula I'm using. And then start to fill that in with details. Vertically, the final position was 0. And the initial position was 0.87. The initial velocity is 0, so this whole term is 0. We can ignore it. And then 1/2 of negative 9.8 times time squared. To solve an equation like this, I'd move the 87 centimeters to the other side, divide, and eventually take the square root. Half of negative 9.8 is negative 4.9. Divide both sides by negative 4.9. And when I take the square root, I get the square root of negative 0.87 over negative 4.9. We get a time of about 42/100ths of a second. Now we can use that time and the information we know horizontally to calculate the initial speed that we need. Again, it looks like we know everything in the so vote for AT&T formula except for V0 in this case. So let's use that and solve for VO. Like before, I'm going to write horizontal. This is a good way of communicating with your teacher what you're thinking and how you're solving the problem. And then write the formula I'm going to use. And start substituting numbers in. We know the final position is 0.27. Notice I'm using only horizontal numbers this time. The initial position is 0. That term we can ignore. The initial velocity is not 0. The initial velocity is what we're looking for, so I have to write V0, but the time in this case we know it's not a variable anymore, 0.42. And we assume the acceleration horizontally was 0, so I can cancel that term out. And this equation is very simple to solve. Simply divide both sides by 0.42. And our initial speed is 27 centimeters divided by 42/100ths of a second. That gives us 0.64. And the units of that would be meters per second, because that's what the standard unit of velocity is, and that's because all the quantities we used in this problem had standard units. To review, in order to solve this problem, we took a couple steps. The first thing we did was listed known and assumed quantities. Then we found time, and then we used time to find the horizontal initial velocity. It's a pretty standard multiple dimension strategy. List the known and assumed quantities, find time, and then use time.